So basically on Monday, what we did was to derive an expression for the so-called D'Alembert theorem. Many refer to the equation that we saw as D'Alembert principle, but to me, and in fact, to most of the literature, is not really the correct way of addressing these equations, because as we demonstrated, they can be derived straightforwardly from Newton's second law. So what we're going to do today is to move on and possibly derive another key, let's say, equation for the formulation, and therefore for the description of the dynamics of a system of multiple bodies, which is Lagrange equations. In so doing, we will try to solve a couple of simple exercises to highlight differences, the pros and the cons of the two techniques. Okay, so if we start over, buongiorno, we have the D'Alembert's principle. Actually, theorem. Stated that if we have NP particles, we have that the sum of the result of external forces over the particle I minus the rate of the linear momentum for the particle I, scalarly multiplied with the virtual displacement of the particle I, was equal to 0. Please do not confuse this capital letter P with this small case p. The former indicates linear momentum, the second position of the particle. And from here, we were able to derive this more compact form. Like so, where this is basically the vector of generalized forces. So this is the vector of generalized forces. And these are the generalized coordinates in consonance. So so this is the vector form in, let's say, componential form. You can also write that our component of the Q, capital Q vector, reads as follows, as to say the sum from I going from 1 to NP of FEI minus capital P I, scalarly multiplied with the partial derivative of the position vector of the I particle with respect to coordinate Qj. Is by definition, right? So from here, what we actually said was that writing this, and let's remember, for every possible dq, for every possible virtual displacement, equaled was a sufficient and necessary condition for zeroing the vector of generalized forces. Okay. We can say that this is, in fact, this condition here implies, or is equivalent, if you want, to the fact that the Qs are linearly independent. if you want, let's write it like this. Q's are linearly let's see what does this mean. Okay, and so let's make an example out of this. So we have Q, the vector of generalized coordinates, which is just composed of two elements, Q1 and Q2. And then we have that, of course, in association to this, the vector of generalized forces can be written as such. Okay, Q1, Q2, capital 1. So D'Alembert's equation becomes as such. Of course, it becomes like this. The Q1 plus Q2 delta Q2 equal to 0. Okay? And do not forget, for every possible couple Q1, Q2. Where, of course, that's actually also include the virtual variation, where, let's remember that delta Q1 and delta Q2 are small, are infinitesimal. And delta Q1 and delta Q2 are compliant with what? With the boundary conditions and the constraint equation. So with the BC and constraint equation. If this is true, we call this a virtual displacement. So this is a virtual displacement as we virtual displacement, and the consequence of this is that, and all of this is true, Q1 equal to 0 and Q2 equal to 2. So this is just rewriting for the case of NP equal to 2 what we have just said. Okay. So let's now assume that Q1 and Q2 are not linearly independent. Okay. So that there is a constraint equation relating, associating, linking Q1 and Q2. So let's assume that we have a constraint equation relating Q1 and Q2. Okay, so it means that Q1 and Q2 are not linearly independent anymore. Okay, if there's a constraint linking them. So For example, we assume a super simple constraint equation. So that our constraint equation is, I don't know, yeah, let's call it like this. Q2 is equal to A Q1. Okay, the most simple that comes into my mind. Okay, so this is our constraint equation. So how does my D'Alembert's principle becomes? So, sorry, theorem. Huh? I also make mistakes. So D'Alembert's equations writes as follows. Of course, Q1 delta Q1 plus Q2 delta Q2 equal, well, Q1 plus A Q2, all of this multiplied by delta Q1 equals to 0, right? This, of course, for every delta Q1 and delta Q2. But let's note that if Q1 plus A Q2 is equal to 0, sorry, this does not, implies that Q1 is equal to 0 and Q2 is equal to 0. Okay? You see? It's straightforward, no? So if the generalized coordinates are not linearly independent, we cannot, in general, say pass from here, so the weak formulation, to the strong formulation. Okay? If you think about this operation, you can think of this in the following terms. Imagine you have a vector. Okay, you have a vector in the 3D space. And then when you write something like this, it's like if you are writing, the vector form, in vector form the sum. So you have the 3 components along the 3 axes, x1, x2, x3, right? And then you have, so the first component A times x1 plus the component along x2, B, x2, plus the component along x3, that you can call C, all right? Well, when you say that if the vector is 0, it means that the components are 0. This is true only if the triad in which you write the vector is made out of what? Orthogonal, that's to say independent directions. Okay? Because if you imagine if, for example, in your triad, one of the 3 axes is just a linear combination of the 2. So that x3, for example, the one that comes out of the plane, actually lies in the plane. Okay? So in that case, you can still write down a component form, okay, of your vector along x1, x2, and x3. But saying that the components along x1, x2, and x3, where x3 lies in the plane of x1 and x2, are equal to 0, does not imply that the vector is 0, because there is still one component, namely the one coming out of the plane, that you are not able to describe with your triad of vector, because this triad is not made out of linear independent vectors. Okay? So the concept here is that you cannot say that, you cannot imply that saying that the components are 0 means that the overall thing is 0, unless the components are projected over a basis. In this case, the basis is made out of generalized coordinates, which is made out of independent elements. Okay. Okay, so again, the take-home message here is that if we want to take advantage of the weak formulation and therefore eventually get rid of this virtual displacement to get something useful, that's to say, again, a strong formulation, we need to rely on linearly independent generalized parameters. Okay? In fact, this is not completely, is not sufficient in the sense that they have to be linearly independent, but they have to be a complete set. What does it mean, a complete set? So in the analogy of the vector description that we were making before, it means that when you want to describe a vector in the 3D space, you need 3 independent vectors. 2, even if you take 2 which are linearly independent, like x1 and x2, they are not sufficient. Okay, so they have to be linearly independent and they have to be complete. Do you know what does this mean? When you have a set of elements to describe a space that has to be linearly independent and a complete set, they are a basis, una base. They form a basis for that space. Okay, is this clear, this concept? So you have to take independent stuff, and they have to be all of them in order to be able to describe all of the possible realization. And so it means that saying that the components are 0 is actually the same thing of saying that the overall thing is 0. Okay. All right. So this is not true. And therefore, again, the Q's must be, if you want, linearly independent. And a complete set. Typically, we refer to this as a complete set of generators as a basis. It's called the basis for the description. What is the space that we want to describe? It's the space of all possible configuration that our system can assume. All right. Okay. Let's make an example. So to clarify further the concept. Let's take into account the case of a frictionless rotating mass. Okay, let's see if I actually have the picture. I should. Yeah, I do. Here you go. So that I don't have to draw anything, luckily. All right, so you see, what do we have here is a super simple system, which is composed of the following. Here we have x1, x2, x3, which is the typical inertial system. Then we have a road indeformable and weightless, which goes from O, the origin of our frame, and rotates in the plane described by the axis x1 and x2. Okay, so in O you have a hinge. All right, so this is a hinge. And again, this road, you can call it as a rail. It's a rail that rotates only about the axis x3. Okay, so it stays in the plane x2, x1, x2. Well, along this rail, there is a mass m. Here I forgot to write the entity of the mass m, which slides frictionlessly along the rail. Okay? And what happens is that this rail is subject to a couple, to a torque T, which causes this rail to rotate about the axis x3. Clear? Super simple, I would say. So, again, this is a rod. And yeah, so frictionless slider. So frictionless slider. And as you can see, we describe the system using, and please note this because this is super important, two generalized parameters. Theta, the angle that the rail forms with the axis x1, and q, which is the distance of the center of mass of the mass, again, which you can call, for example, here, g, and the origin of the inertial mass, of the inertial system. Okay, now, apart from everything else, just note one thing here. You see here, we have a lot of constraints. Because, okay, in terms of constraints element, of constraint element, we have two constraint elements. We have a hinge, and here we have a tray. A frictionless inner, a frictionless. And so we have additional constraint equations, right? But if we were to choose as coordinates to describe the motion of the system, like the Cartesian coordinates, x1 and x2 and x3, we should have connected this set of three coordinates through the implementation of the constraint equations of the hinge and of the tray. Okay, as we have seen. Now, what we have done, instead of using the Cartesian coordinates, we have described the state of the system using only two coordinates, which is theta and q, which completely define the state of the system, and this is the super important thing, do not require or completely satisfies already the constraint equation of the system. Okay, because theta can take whatever value, q can take whatever value. Once you have defined a status, defined again with the couple theta q having some values, you have defined completely the state of the system, and this state, this couple determines all of the admissible states for the system. So you see here what is the real advantage of using generalized coordinates, which are also referred to as Lagrangian coordinates, that you can define them so that they automatically satisfy the constraint equation, and you do not have to associate the constraint equation to the equation of the dynamics of the system, okay? Because they are already satisfied. So you define the equation so that the constraint equation are already automatically satisfied, okay? And you can get rid of, you can forget about them. That's the advantage of, because otherwise one would say, okay, but I mean, we are in the 3D Cartesian space. Why don't we use x1 and x2 and x3, right? That would be the most immediate way of describing the system. No, we went through all of this concept of generalized coordinates because this way we automatically determine all of the possible states that the system can assume without any effort associated to the constraint equations. Okay? Okay, this is something that I wanted to stress out because it's important. All right, so what I did here, so here, again, let's actually stress this out. So here we have a tray, yeah? This is a tray. Okay, so the two constraint elements that we have are the hinges and the tray. Okay, so here on the right, what I did was to basically represent a free body diagram of our mass. So just a second. All right. So here we have all of the forces which exist in our system. We have the contact forces at the hinge. The hinge can express which forces? Translational forces, and that's it. You cannot have a torque associated as a constraint to a hinge because the element must be free to rotate. Okay. And then what else do we have here in on the mass? We have basically the weight, m times g. We have basically two contact forces which are equal and opposite in sign. Okay, because one is the force, the contact force that the rail exerts on the mass. Okay, so the application point is the mass. The other one is the force that the mass exerts on the rail, okay, which is equal and opposite in sign, and has application point on the rail. Okay, so the point of application of these two forces are different. All right. Okay. And then what do we have also? We can also express this torque, if you want, as what? As the product of a leg and a force. So a moment, a torque, is a force times a distance, appropriately defined. So in order to simplify this system, let's define this force F, which is actually applied over G, the center of mass of our force, of our particle, sorry, of our mass, as a product with the distance, the vector Q, of the vector X between O and G. So that, to be clear, we define the vector X so that its module is Q. Okay? Yeah, so here see we have G. Okay. Yeah, of course, here we also have theta. So this is our theta. Okay, so we have that T, our torque T, can be expressed as what? As X, the vector X, vector product, the vector F. Okay? Right? This should be crystal clear. So let's try to find out what are the components of this F so that this vector product exactly equals our torque T. How do we do that? Well, we do it like this. Oh, I typically do it like this. So you have the component of X. What are the components of X? You can derive it from here in X1 and X2. So you have that X has the following components. You have Q cosinus of theta. This is the projection over X1. And then you have, of course, Q sinus of theta. And then you have 0. Right? Okay. Then they have to be multiplied by the fx, which is what we want to find. Then we have fy, and then we have fz. And all of this must equal t. And the components of t, which are the components of t? They are 0, 0, t, right? Because t being the torque, about the axis x3, it has only a component t aligned along x3, right? So if you ever use this, there are a lot of ways to implement a vector product, but here we have that. So if you want to get the third component, which is the only one which is missing, you have to basically cancel out this, and then you have to make this vector product, right? So you have that basically q cosinus of theta times fy minus q sinus of theta times fx is equal to t. Oh, wait. To t, right? And then you have, so this is along z basically. And then you have that, if you have, for example, this, you have the q sinus of theta times fz minus 0 has to be equal to 0, right? And then you have that q sinus of, q cosinus of theta times fz minus 0 is equal to 0. Okay, so this is what the three equations that we have to find fx, fz, and fy. Okay, it is straightforward to get from here the following. Fx, if you solve these three super simple algebraic equation, you get that fx is minus t over q sinus of theta. Fy is t over q cosinus of theta. And fz is 0. In fact, if you make the vector product between this vector and x, you get t. Okay. All right. Then the resultant of external forces that we call Fe. What is it? Our Fe is, F, which is this force that we just estimated, plus what? Plus m times g, the weight. These are all the external forces that we have. And if we sum this, we get minus t over q sinus of theta minus mg plus t over q times cosinus of theta and 0. Okay? All right. One additional point. If you look at the description of the contact forces that we've done in the previous image here, do you think that we can consider our system as worthless in terms of constraints or not? We saw it last time, no? Or I think even the previous day. What does it mean that the contact forces are workless? They do not basically make any work over virtual displacement. So virtual displacement is an admissible displacement, small but admissible. So it means that when it rotates a little, you have to see if the constraint basically have a positive or negative or zero work over that displacement. So if this rotates, basically forming circumference over G, because this is the only thing that can make, and then it also slides as well. You see, you have the contact force. So here you have contact forces, but this is a hinge, so it doesn't move. So the work associated to these forces is zero, because basically there is no motion on the application point of these forces, first. Second, these other contact forces which act on G, which is the center of mass of our, let's say, of our mass eventually. You see, what is the relationship with regards to the motion and eventually to the overall contribution of the work associated to them? Huh? You have an idea? There is no friction, huh? So these are the only forces associated to the contact, to the constraint. I would say it's zero. You don't see it? The question is, can we assume that our system is workless in terms of constraints, that the constraints are workless? I would say the hinge, we can fairly assume it's workless, because the displacement point, the displacement of the application point of the forces associated to this constraint is zero. So the hinge does not move. So the application point of the contact forces does not move. So the work associated to the contact force of the hinge is zero. Now, what about the tray? So the tray has no friction associated to it. So there is no force along this sliding of the mass over the rail. Okay. The only thing that we have is this orthogonal component. So in theory, when it slides like this, the sliding motion is perpendicular to the line of action of the force. But the thing is that it also rotates. So the trajectory of this particle, in theory, can have some non-null projection over the line of action of the forces, right? But we have two forces, which are exactly equal and opposite. So what is the overall contribution that they can make in terms of virtual work? Is equal and opposite, so it's zero. So our system can be assumed to be as having workless constraint. Is this clear? No? But this is important, huh? Okay. Because again, here now we have to write the virtual world theorem eventually, and so D'Alembert equation. So we have to see if we can write D'Alembert equation, and D'Alembert equation can be written only if the constraints are workless, as we have assumed. As workless constraint, and therefore, let's say that W is equal to 0. Okay, so it looks like it's not stuck. I'm looking from here. It's a nice check.
Bisogna sempre guardare tutto l'insieme, perché se noi consideriamo solo tipo l'asta, in quel caso
Of course, yes. Yes.
la forza dell'input la perché.
Esattamente. Okay, move on. Let's actually now, so we have seen the external force, we have seen the contact force. Now what do we miss? Inertia, right? So let's calculate the rate of linear momentum. Okay, which is P dot, capital P dot. Okay, the position of the particle. What is it? It's, which we call P, is equal to the following. Cosinus of theta, sinus of theta, and 0 multiplied by Q. So it's basically the projection over x1 and x2. Therefore, my Q dot with the chain rule assumes the following values. Sorry, it's not Q dot, it's P dot. So it's theta dot applied over minus sinus of theta, cosinus of theta 0, and Q is still here, plus the same of before, cosinus of theta, sinus of theta, and 0, times Q dot. Okay, well, I think this is simple. I just applied the chain rule over this product. And therefore, we have that P, capital P, is equal to M P dot. And therefore, P, capital P dot, so the rate of the momentum, since the mass is constant, is just like this. Okay, now you can just derive it another time, this, with respect to time. So if you trust me, this writes as such. You can verify the calculation at home. I invite you to do so. Which multiplies minus sinus of theta, cosinus of theta, and 0, plus m q dot, which multiplies cosinus of theta, sinus of theta, and 0. And m theta dot squared q, which multiplies minus cosinus of theta minus sinus of theta and 0. Okay, so this is the rate of the linear momentum. Okay. Now what we have to do is to write the virtual work associated to external forces and inertia. Okay, let's do it. Delta WE and delta WI. So delta WE what is it? Is Fe matrix product or scalar, if you want. Okay. Delta P. And if you do this, you get minus mg sinus of theta delta q plus t minus m g q cosinus of theta delta theta. Okay? While our delta wi, which is capital P dot transposed applied over delta P is equal to what? Well, again, it's 2 m q dot theta dot plus m q squared theta double dot multiplied by delta theta plus q double dot minus m theta dot squared q applied to delta q. Okay? So remember that delta P is basically just, it works like a derivative sign, you know, the delta. So is minus sinus of theta cosinus of theta and 0 q delta dot plus cosinus of theta sinus of theta 0 delta q. Okay? So this is just the definition of the virtual variation of P, which is, again, the virtual operator acts like a total differential. The last thing here that I would like to highlight to you is the following. You see here that we have a pattern. So we have something associated to the Q, and something here associated to the Q, where Q here is the distance of the mass from the origin. Okay? And then we have this other term here, which is associated to the other parameter, the angle, here and here. See? Okay, now let's remember D'Alembert's principle. Huh? Can I slide it? Sure. Okay. So from D'Alembert's theorem, what do we have? Again, the sum of I going from 1 to MP of Fe I transposed applied over the Pi minus P, capital P, dot I also applied to delta Pi. All of it. And this, for I equal to 1, is Fi T applied over delta P minus capital P dot times delta P, transpose as well here. And this is equal to 0. Q transposed over dq equal to 0. Okay? So why did I write this? Because you see, we already have this. If you look at what you wrote in the previous slide here, you already have, you see this, something which is multiplied by the q and the theta. Remember that delta q vector is just delta q and delta theta. Okay? This is how it's done. So if I want to write this, so you see here we have Fe delta P, P dot delta P. These are actually what we were missing. So this is this. See? And this, oops, here is this. See? So if we substitute in here, we can get Q. So what we get eventually is this. T minus m g q cosinus of theta minus 2 m q dot theta dot minus m q squared theta double dot times the theta plus m theta dot squared q minus m g sinus of theta minus m double dot q. All of this multiplying the q, and this has to be equal to 0. And this, in fact, is equal to q, let's say, delta, if you want to call it like this, times delta, the delta, plus capital Q, times delta Q. Okay, so this is this, basically, written in componential form. All of this means that this first here is our first component of the vector of generalized forces. So this is our q theta here, you see? Correct? And this second here is our second component of q. Okay? Now, what is the rest that we have to do? We have to pass from here to the equations where we say that this, writing this, is the same as stating that this and these are independently 0 if these two coordinates are linearly independent, as we have said at the very first of the lecture, part of the lecture. And so we have two equations. I'm gonna do it right now, and then we're done. Okay. So, oops. Saying that Q delta times delta Q, delta theta plus Q times delta Q is equal to 0 is the same as writing that Q theta is 0 and QQ is 0. Why? Because Q and delta Q and theta, sorry, are linearly independent. And therefore, eventually, we have the two equations. That's to say that M times Q minus M delta dot squared Q plus M G sinus of theta equals 0. And then M Q squared theta dot plus 2 M Q dot Q and theta dot plus M G Q cosinus of theta minus T is equal to 0. 2 degrees of freedom, Q and T, 2 equations. These are the equations of the dynamics of this system, derived using D'Alembert's theorem. All right? Yeah, here I'm missing a double dot. And so you see here, for example, this first equation is the equation of the dynamics of what? So they are coupled because Q and theta are in both equations. But the first one is the one that contains Q double dot. So this is referred to as the equation of the dynamics of Q, because it tells you how Q dot and therefore Q evolves in time. Okay. The second is the equation of the dynamics of theta, of the angle. And in fact, you may notice one important thing, interesting thing, that Q, the T, the torque, only acts on the dynamics of theta, of the angle. But the angles eventually is also present in the first equation. So eventually the torque, as it should be, as it can be expected, also influences the evolution of Q. But from a direct point of view, you can only find the torque in the equation of the evolution of theta, of the angle. All right? Okay, so now we are going to introduce another very important concept in the course, which is derivation of Lagrange equations. Okay, so I ask you to be focused for some more minutes. And I'm not sure if we're going to be able to do it today, but the idea is the following. Let's derive Lagrange equations and re-perform this exact exercise, and you will see that it will be much, much easier to solve. That's the idea. And even if this is only, you saw, it's just one particle doing some very simple motion, you saw how nonlinear and complex the equations are. And this is just one body. Okay, no worries. Lagrange equations. So to derive Lagrange equation, what we will basically do is just go through some manipulation of the virtual work associated to inertia forces, and that's it. So this is, for what we have already written, is just the sum of mass I, of the particle I, times the double derivative with respect to time of the position of the particle I, right? Which is the rate of the linear momentum. Sorry, of course, the virtual, virtual. Okay, so we now express this in terms of generalized coordinates. And this becomes mi p double dot I times the derivative of pi with respect to qj times delta qj, as we have already seen. Now we have that the sum over I going from 1 to np of mi pi double dot times the pi over the qj can be written as such. It's the sum from I going from 1 to np of the following: the time derivative, total time derivative of mi pi times the pi over the qj minus mp dot scalar product dt of the pi over the qj. So it may seem complex, but what I've done here is just saying that this here is the result of deriving everything, all of the product with respect to time, and then taking one part away of the product. This is it, okay? If you derive everything with respect to time, then you remove this part, you get this. I invite you to check it. Yeah. Yeah, correct. Very nice. Yes. Okay. Let's keep going. Let's introduce another bracket. The time of what? Of the derivative, the partial derivative with respect to q j dot of what? Of 1 over 2 mi pi dot transposed apply over pi dot minus the derivative with respect to qj of 1 over 2 mi pi dot transposed over pi dot. Okay, so I basically brought the partial differential sign outside. And introduce also a partial derivative with respect to time of generalized parameters. Now you see that we have the same, very familiar, I guess, quantity in between the round brackets that we call t. Ti over the qj dot minus the ti over the qj. Okay? Where ti is, by definition, 1 over 2 mi pi dot transposed applied over pi dot. What is it? This one is the kinetic energy of the particle I. Okay. All right. Now the most annoying part, it's over. Okay. But remember that this that we have written is just the first part here. So in all of this. So let's rewrite my virtual variation of the inertial work. Okay. So my delta Wi becomes what? Delta Wi is equal to the sum of the j and from 1 to n. Remember that np is the number of particles, n is the number of the generalized coordinates. It's two different stuff. Okay. I going from 1 to np. Well, let's just rewrite what we have written before. So dt of the ti over the qj dot minus the ti over the qj times delta qj. Okay. Okay. Now, if we define what t equal to just the sum of I going from 1 to np of ti, this is the total kinetic energy of the system. We can rewrite in a very nice form. That's to say the following. D over D Q dot vector. Oh, sorry. No, sorry. The T over the T over the Q dot vector. Minus the T over the Q. Applied over Q. You see? Please note one thing. When you derive, we already said that, when you derive with respect to a column vector, you get a row vector. Okay? So the t, which is a scalar, when you derive it with respect to a column vector, you get a row vector, and therefore this applied to this makes a scalar. Okay? Because here you have a matrix multiplication. There is no scalar product here at the end of the square bracket. Okay? And so therefore, D'Alembert's equation becomes delta W, which is delta WE minus delta WI, because again here we have workless constraint, so there is the C part is not there. D over dt, or dt over the Qj dot minus the derivative of t with respect to the Q minus QE transposed applied over the Q is equal to 0. Because here, remember that this is QE transposed applied over the Q. Okay. This form here, if you happen to find it, is referred to as D'Alembert-Lagrange equation, because it's kind of something in between. Okay. Now we still have to do something. We can take into account the fact that the Q's are linearly independent and write this in the strong form. Okay? Let's do it, and then we're basically done. Take advantage of the Q being linearly independent. And that's an hypothesis. This is a super important hypothesis to write down Lagrange equations as well as D'Alembert's equation. And therefore, we pass from this to this. Yeah, let's write it like this. An additional thing that we can do is to divide our QE into a conservative and a non-conservative part. Okay, so you have that QE is just QE C, this is the conservative part, plus QE and C, which is the non-conservative part, where QE can be written as the partial derivative with respect to the Q the transpose, in fact, of U, where this is by definition, if you want, with U being the potential mechanical energy. Okay. If they are conservative, they allow a potential energy to be defined. While this is typically what? Friction, for example. Okay. And therefore, we're done. Let's put everything together. Can I slide? Yeah, sure. Sorry. Yeah. Okay. This depends on the convention that we use, but typically it has a minus sign in front of it most of the times. Okay. Okay. So if this is true, so our equation becomes the derivative with respect to time of the t over the q dot minus the t over the q plus the u over the q. This here is minus QE conservative transposed equal Q external transposed non-conservative. So I define the Lagrangian function you maybe already have heard of it. which is L, which is typically a function of Q dot and time, as T minus U, the difference between potential energy and kinetic energy. And therefore we get d over t of dl over dq dot minus dl over dq equals to q e and c transposed. And this is Lagrange equation. Or one of the form of Lagrange equation. You get many of them. Sometimes you write it in terms of kinetic energy, and that's it. You don't actually introduce the Lagrangian function, but sometimes you can find it like this, so it's useful to know. Esattamente, è fondamentale questo. So there is no dependence of U here. Let's actually write it. Only of Q and time. Okay, so not Q dot. Otherwise, I could have not written this, because this would have given me an additional term. Okay, since L also has U inside of it, right? Okay, so let's retake into account the exercise, and you will see that we will do it in a couple of minutes using this. While it took us half an hour and more at the beginning of the lecture. Okay. And then we're done, I promise. Okay. Same as previous example. No? So you always have this exercise, always the same system. So in this case, it is useful to write the position P of the particle, P dot, the velocity, which we already have written as theta dot. Now if you go and check sinus of theta, cosine of theta, and 0 times Q plus cosine of theta, sinus of theta, and 0 times Q double dot. Sorry, this is Q dot. Yeah, of course, it's Q dot. And typically can rewrite this as a matrix product like this: minus Q sinus of theta, Q cosinus of theta, cosinus of theta, sinus of theta. In all of this, multiplying the vector theta dot and Q dot. Okay. So that our P dot is just a matrix that we can call B times Q dot, where this is B, basically. Now let's calculate the kinetic energy of the system. The kinetic energy of the system, by definition, it's 1/2 m p dot transposed apply over p dot. Okay, we only have one particle, so there are no indices here. And this can be written, introducing this, as 1m q dot transposed, b transposed apply over b, applied over q dot. Okay? And if you do the math, and it's super simple because the product of B over itself is almost an identity matrix if you do it. It's a 2x2 identity matrix almost. Becomes 1/2 m theta dot squared q plus 1/m q dot squared. You see, it's kind of simple, no? Here you have that the kinetic energy of the system is associated to two motion. The linear motion over the rail, q dot squared, and the rotation when q is constant. So when it does like this, when it does like this. See? Pretty simple. Now all we have to do is this. We remember that dWe, the work of external forces that we wrote like this, if you go and check, our q theta is just t minus mg q cosinus of theta, while our qq is minus mg sinus of theta. Okay? So using Lagrange equation, so all of this is conservative already. So QE, which is Q theta and QQ, is our conservative part. So all the forces here are conservative. There is no friction, there is nothing. Now, all we have to do is derive, and that's it. So if we derive with respect to theta, the first of the two generalized coordinates, we get d over t of dt over d theta dot minus dt. You see, now we are using one in a different form, the one that we have seen previously, of d theta equals q theta, right? And then we have to do, for the second equation, we just have to take the second derivative. Okay? If you just take the derivative of this t, which is super simple, we have just this one t is super simple. We have to derive with respect to t dot here, q dot and q, and that's it. And if you do it, you eventually get these two. Which I invite you to check that they're exactly the same as before. I think it's quite easier now, using Lagrange equations. We only have to take a couple of derivatives with respect to time or the generalized coordinates, and we get the same exactly equations as before. In fact, maybe tomorrow, I don't know, or next week, we're going to see that there is even a shorter way to solve this exercise, and we will see it using the so-called Keynes equation. Equazione di Keynes. Keynes equations. But this is another story. There, let's say the formulation to arrive to the final form of the equation, which is super, super simple, it's a little bit annoying, but it's worth it. And we will see. Okay, so that's it. This is it.